The introduction. Let me share my screen. Okay, I hope you are seeing, right?
Yes, perfect.
Okay, great. Um, so this is a very basic and introductory tutorial. When I was preparing these slides, my idea was to provide an overview of my impression of this area and illustrate some formal models and languages using some toy applications, some puzzles, and some classical examples from the literature. So this is a very basic presentation on formal models. So if you have any question, please do let us know. Okay, so let's start. So I think it's quite clear for all of us that we live nowadays on a connected society that is basically software based, uh, but we all share our disillusions when some software and systems don't work as expected. And the idea, my impression of this era of formal methods, the main motivation is to provide enough evidence in some situations such that you can increase the confidence you have on the system or software you are using. So, formal methods have a very important role when you are seeking a high trustworthiness levels. Here, I would like to quote this definition from Formal Methods Europe, that despite the name is a worldwide association uh, of researchers and practitioners on this area. So if you are a newcomer and you are getting even more interested about this subject, I suggest you subscribing to the FME mailing list. So the definition of formal methods provided by FME is that formal methods are mathematical approaches to software and system development which support the rigorous specification, design, and verification of computer systems. So the main keyword, I would say that's rigorous. So we are talking about uh, a number of techniques, but all of them have this central notion in mind. So you should provide support to specify, design, and verify computer systems by rigorous means. Uh, this picture is my personal impression of the area. Uh, so the central piece for me is that you need to have a precise and clear specification of the system you want to verify, analyze, simulate, or the property you want to analyze. So the central piece is the so-called, you need to have a formal model. This formal model can be created by the user of the technique. So in our previous session, when Sérgio was presenting his work, he said that at the first time the SMV model was created by them, but in practice, the practitioners would not create this model because they are more familiar with Simulink models. So the formal model can be itself derived from other models. So you can also, we have some work where the formal model is derived from natural language requirements, for instance, or some structural requirements. There are also possibilities for generating these formal model from actual code, let's say Java code, C++ code. And this translation from all the artifacts to a formal specification, to a formal description of the system or property, this can be performed manually or automatically. And when you are doing this, a typical question that arises is, do you have any guarantees about the preservation of the semantics regarding the original and the derived or created model? Because when you have a set of requirements, or when you have a code, or you have a Simulink model, for instance, you have an underlying semantics that is typically informal. And when you create a formal specification, which has a formal semantics, how do you assess whether uh, this model properly describes the previous artifact you had? So this is a typical issue, a typical question that typically arises when you are working with formal methods. Well, when you have this model or this precise specification, we have many different techniques to perform a variety of analysis regarding this model. So I would group the possibilities into four classes. The first one is you are going to use this model to perform some kind of animation or simulation. This animation can be performed by the user, so guided by the user. So the user is going to control how the model is executed, or this can be performed randomly. It's also another possibility. And animation is a very important possibility in terms of validation. So as I said before, suppose that you create a model and you hope that this model properly reflects the semantics of your original specification. So the first thing you should at least try to do is to simulate this formal specification, if it's executable, to check whether the simulations are consistent with your interpretation of the expected behavior. So, in other words, are we creating the right model? That's a question that can be partially answered by animation techniques. Another class is verification, and we have lots and lots of works supporting verification of formal models. This verification can be performed manually, let's say by writing a proof by hand, or even by writing a text that provides informal arguments to show that some property is true. You can also mechanize part of this process using some proof assistant, like Coq and others. You can even try to go further and try to use some tool that hopefully will automate all of your proof, so the proof is carried out automatically with no user intervention. When it's possible, it's even a dream. And we have these tools called theorem provers that try to provide means for doing this again when it's possible. And another classical technique, verification technique, is checking. So you basically translate your formal specification into some transition system, and you verify this property by uh, performing some kind of analysis on this system. So checking whether this system, whether some properties hold on this system. Another possibility is related to generation of other models, or even code generation with formal guarantees. So suppose you have a precise specification of the expected behavior, and there are some techniques that you can use, for instance, to derive a C code from this specification with guarantees that the semantics of the generated code properly reflects the semantics of your formal specification. And a last class, in my opinion, I would say that's probably one of the classes that is not very explored yet. That is providing means for visualization of formal models. What I mean here is creating graphical user interfaces such that you can present your prototype or even your tool to an end user, but this graphical user interface would be running not on a Java or C++ implementation, but it would be running the actual formal model. So we have some tools that support this idea. So this is my personal impression of the area regarding the possibilities of using formal methods. So in the next slides, I would like to present you with some concrete examples. So if you have never seen uh, practical examples of formal methods, I would like to show you at least four very simple examples. I'm not an expert on these formal methods. I'm sure that we have some attendees in this session that are much more specialists than me on them, but I will try to explain the main ideas behind these formal methods and tools. So in my notation here, behind the bar is the name of the language or the notation, and after the bar, you can see the name of some tools that supports this formal model or this formal language. So I'm going to start with a language and a method called B. And to illustrate this method, this language, I will use the Tower of Hanoi puzzle that may be familiar to all of you. So in this puzzle, you have the classical one. You have three pegs, a number of disks, and you want to move all disks from the first peg to the last one. But you have a constraint, and a constraint is you cannot place a bigger disk over a smaller one. So you need to perform some kind of some kind of movements such that in the end all disks are on the last peg, but respecting this constraint. I'm going to illustrate how to solve this puzzle using this language B and supported by two tools, the ATLRB and the ProB, which is the last one is a model checker for languages like B. So here is my B specification of the Hanoi problem. And now you're going to see the idea of specifying a problem in a very precise way. I'm going to model the state of my system, of my problem, using a function. So I have a variable called Hanoi, and this variable is declared as a total function between the numbers 1, 2, and 3, and a set of numbers also ranging from 1, 2, and 3. So here, my abstraction is the numbers in the domain represent the pegs. So I have the first, the second, and the third peg. Here I'm writing a specification considering just three pegs, but we can generalize these for an arbitrary number of pegs. I just wanted to keep it simple. Uh, and the intuition of the codomain is the numbers in this case represent the disks. And if I say that I have a pair in Hanoi mapping, for instance, 1 to a set with the numbers 2 and 3, it means that in this peg, I have the disks 2 and 3. And in my case, I'm going to use smaller numbers to smaller disks and bigger numbers to bigger disks. I'm also assuming here, since this is a constraint of the problem, that in every peg, the, the topmost disk needs to be the smaller one. So I'm not modeling my codomain using, for instance, sequences, but only sets with no order notion, because it's enough for what I want here. So I have here some predicates formalizing some constraints of the problem. So for instance, I don't have disk repetition between pegs. So for all two pegs that are different, the disks on this peg is different from the disks in the other peg. So the intersection between the disks on these two different pegs need always to be empty for any two arbitrary different pegs. I will skip this predicate. I will come back to it later. So in this model, I could say that initially I have this situation here, where in the first peg I have the three disks, so the disk number 1, disk number 2, and disk number 3, and the other pegs are empty, so they are mapped to the empty set. And now I can formalize the action of moving disks between pegs using operations in B. Different from many programming languages, when you are in such languages, when you are creating a method or a function, you typically just write the behavior. So what should be done when this operation or this function is executed. Here in this formal model, besides specifying the behavior of the operation, I can also state the assumptions I'm relying on when executing this operation. In other words, which preconditions need to hold such that I can perform this operation safely. By safely here, I mean satisfying the constraints of my problem. So what I say here is that move is an operation that takes two arguments, from and to, where from and to are natural numbers, but they should be a member of the domain of Hanoi. In other words, from and to needs to be a number ranging from 1 to 3. Besides that, from and to needs to be different. So it doesn't make sense to remove a disk from a peg and put it back on the same peg. So from and to need to be different. More than that, I cannot move a disk from a peg that has no disks. So I say here that if I apply the function Hanoi to from, this will return the disks mapped to from. And I'm saying here that this set cannot be the empty set. And in this last precondition, I encode the constraint I mentioned before. So when I'm moving a disk from a peg called from to a peg called to, I'm always moving the smaller disk from and put it on the top of the peg 2. So in other words, I say that the smaller disk from the from peg needs to be lower than the smaller disk from the peg 2. So basically, these constraints encode that restriction I mentioned before. So if all these conditions are met, I can safely perform the operation move. And since Hanoi is defined as a function, changing the state of my system is encoded as updating this function. So in this case here, I use this operator to say that now Hanoi is this function updated by this definition here. And basically what I'm saying here is that the mapping from the domain, from the number from, is updated by removing the smaller disk, and the set mapped to 2 is updated by putting inside this set the disk I removed from the peg from. So as you can see, uh, in this abstract specification, I'm not worrying about how I am going to implement this. So I'm not worrying about what are going to be the user data structures. I'm going to implement this mapping using, let's say, red-black trace. I'm going to use hashing. Here I'm modeling the problem in a more abstract perspective. So provided that you have this model, you can use these tools, Atelier B and ProB, to perform a number of analyses. For instance, you can use ProB to create the state space of this problem. So in this configuration we have here, the state space of this problem comprises 28 states and 79 transitions. In other words, 79 different ways of performing uh, moving disks between pegs. Using Atelier B, I can perform all the analysis like proving that there is a solution and proving all the properties I want to prove regarding this problem. Particularly, I can use this tool to prove that all properties stated as invariant, which means that these properties should hold on every state of my system. So I can use, for instance, Atelier B to perform this proof using a proof assistant where part of the proof is performed automatically by some solvers, whereas in some situations you need to guide the proof as well. You can also use ProB to perform the same analysis but using a different technique, but by using model checking. So this last invariant that you have here on line 16 can be used to find a solution to the problem. So what I'm saying here is that there is no state where the first and the second pegs are empty and all disks are in the last peg. So if I use some of these techniques, particularly ProB to check the invariants, what ProB is going to do is it's going to create the state space. It will iterate over this state space, and it will check whether the stated properties, the stated invariants, hold on each reachable state. And as it turns out to be, there is a solution for this instance of Tower of Hanoi, and ProB is going to be able to find a sequence of operations that would drive the system from the initial state to the state where this property is violated. Okay, so that was my first example. My second example uses a different language called CSP and a tool called AFDR. To illustrate this language and tool, I'm going to use a classical problem called the dining philosophers, which is a metaphor for the idea of concurrent systems. So the problem states that you have a table, you have a number of philosophers, and each philosopher sits on the table, then it eats, and after eating, it gets up and uh, sits again later and repeat this process many times. The trick here is that to eat, they need to get a fork, let's say. But since the table is a round one, you can see that each fork is shared by two different philosophers. So this is a metaphor for a situation where you have a computer system or a software where you have many processing units or many threads, many components, and each component needs to perform some task. But to perform this task, this component relies on shareable resources. And when you are designing concurrent systems, you need to always be aware of avoiding situations where you have a deadlock in your system. So a situation that typically, as a consequence of the shared resources, a state from which you can no longer progress, you cannot do anything after reaching this system. So this problem can be specified in this language called CSP, as I'm showing in this slide. So suppose I have here a number n to define the number of philosophers I have around the table. And I have two sets, field names and fork names, and they basically range from 0 to n minus 1. Here I declare channels to denote the actions performed by the components of my system. So as I said before, each philosopher can sit, eat, and get up. And in this declaration here, I'm saying that these actions are indexed by the ID of each philosopher. Besides that, regarding the forks can be picked up and put down by the philosophers. And in this case, these actions are indexed by the ID of the philosopher that is picking or putting down the fork, but also an ID of each fork. The behavior of each philosopher can be defined using a process, as it's called in CSP. So, uh, an arbitrary philosopher, it first sits down, then it picks, so this philosopher picks one fork and another one. So it picks, for instance, the fork I and the fork I plus 1 mod n, since we are in a round table, so we need to perform this modulus operation. After eating, it put downs the forks in reverse order. So it put down first the last fork, he picked it up, then the first one, then he gets up and behaves again as a philosopher. It means we have a recursion here, so it can sit, pick, eat, put down, and get up again. Each fork has an option, since, as you can see in this image, since each fork is shared by two philosophers, each fork has an option. It can be picked up by, let's say, philosopher number 2 or by philosopher number 3. So in this formal specification, this symbol here that denotes external choice, it says that this fork can be picked up by philosopher I, and if it's the case, it needs to be put down by the same philosopher, then it behaves as fork again. However, another possibility is the philosopher being picked up by a different philosopher, so the other one. And to finish my formal specification of this problem, I can say that the philosophers is the collection of all philosophers I have, and there is no synchronization between them. So I use this symbol here to denote that each philosopher is combined with the others using an interleaving operation. And I can say the same about the forks. So there is no synchronization between forks. However, when I have the system, philosophers need to synchronize with forks. And it means that a philosopher can only pick up a fork if the fork is ready to be picked up by that philosopher. So in this language, this code here is saying that these two processes, they are running parallel, but they need to synchronize on all events performed on these channels, the channels peaks and puts down, which are the channels that control the use of the forks. And then I can use tools like FDR to assert whether the system is free of deadlock. And as it turns out, in this situation, we have a deadlock that is basically suppose that this philosopher picks this fork, and the same for all philosophers, we are going to reach a state where each philosopher has a single fork. All of them will be waiting for the second one, but the second fork is not going to put down the table because everyone is waiting for a fork. So this is the deadlock state reached by this that can be reached by this example. So there are a number of solutions for this problem. So you can, for instance, use a butler to resolve the deadlock. You can also select one philosopher to uh, behave in a symmetric way. So instead of picking first the I and then I plus one, it picks first the I plus one, then I. So in other words, instead of picking up first the left fork and then the right fork, it suffices to have one philosopher that will pick up first the right fork and then the left fork. So this is a kind of analysis that you can perform using FDR. You can also use this tool to visualize the state space. As we know, this is a problem where the number of states grows exponentially. So if we have two philosophers, we have about 30 states, which is depicted in this figure. But if we have four philosophers, for instance, we have more than 1,000 states and more than 4,000 transitions. Okay, uh, another language and tool I would like to mention here is UPPAAL, which is a language for specifying and analyzing systems using timed automata. To illustrate this tool, I'm going to use another toy example, which is another puzzle called the bridge crossing puzzle. So suppose that you have a bridge. You have four people trying to cross the bridge from the left to the right, and each person has a different speed. Besides that, let's say that the bridge is fragile in such a way that the maximum allowed number of people crossing the bridge at the same time is two. So, for instance, three people cannot cross the bridge at the same time. At least you want them to arrive, if at least you don't want that then they're going to arrive safely on the other side. And a last restriction is that it's dark and you have a shared flashlight, and you can only cross the bridge by carrying the flashlight. And it means that if two people, for instance, cross the bridge with the flashlight, someone that needs to come back to pick other people from the left side. So you can model this problem using automata. In this case, we are going to have one automaton for each person, besides another automaton for the flashlight. The automaton for each person can be seen on the left. The initial state is this one with an inner circle, and this is called the unsafe state. And we want to reach the safe state, which means the right side of the bridge. So you have transitions between the states, and the transitions may have guards that are denoted here in green. This variable L represents the side of the bridge where the flashlight is. So if the flashlight is on the left side of the bridge, L is equal to 0. If the flashlight is on the right side of the bridge, L is equal to 1. So if I want to go from the left to the right, the first requirement is that the flashlight needs to be on the left side of the bridge. So if this is the case, I try to pick the flashlight. But to do this, the flashlight needs to be red to be taken. So this exclamation mark here is used to synchronize with the event with the interrogation mark. So if one person is on this state and he wants to perform this transition, the flashlight needs to be on a state where take interrogation mark action can be performed in such a way that we synchronize on both of them. So after taking the flashlight, we reset a clock. So Y is a clock, and delay is a parameter of this timed automaton, and it encodes the time required by crossing the bridge. So I mean, the time required by this person to cross the bridge. So after taking the flashlight, I reset this clock, and only after Y is greater than the delay of this person, I can reach the safe state. And to reach the safe state, I also need to synchronize on the release event. It may be the case that even after reaching the safe state, this person will need to go back to bring all the people to the right side of the bridge. So we also have transitions moving from the safe state to the unsafe one. The difference is that in this case, to do this, the flashlight needs to be on the right side of the bridge. The automaton of the flashlight encodes the following behavior. This is initial state, so the flashlight is free. No one has taken it. If someone takes the flashlight, it reaches an urgent state, which means that another action needs to happen with no time delay, so in instantaneously. So the flashlight can be taken by two different people, meaning that two people are going to cross the bridge sharing the flashlight. But someone can also move to the right side of the bridge, uh, carrying the flashlight by itself. So just one person crossing the bridge. And this action here basically updates on which side the flashlight is. So initially L is equal to 0. If you take the flashlight, when you release, it means that you have reached the right side of the bridge. And now L is equal to 1 minus its previous value. So if it was initially 0, it's now 1. So the flashlight is on the right side of the bridge. So you can use this tool called UPPAAL to create many instances of these automaton. So in this configuration, you are going to create 4 instances of the left automaton, in addition to an instance of the right automaton. And the collection of these 5 timed automata are going to describe the behavior of your system. And just to mention, and using UPPAAL as the other tools, you can perform a number of analyses. So you can perform animation, you can write predicates using linear temporal logic, for instance, and you can use these to check whether these properties hold or not. And the last example I would like to share with you is a tool called Z3. We are going to have a keynote in SBMF by Nikolai, one of the main developers of Z3. And Z3 is a solver where you can write a number of constraints using these SMT lib2 uh, is a language that's a standardized language for SMT solvers. Uh, and this language uses a prefix notation. So let me go through the example. What this code here is stating is that suppose that you have two Boolean numbers, two Boolean values, sorry, P and Q. And the first constraint I'm coding is that P needs to be equal to Q. When I run this command checksat, the tool checks whether there is a valuation for P and Q that will satisfy this constraint. And when I execute the command get model, the tool shows a possible solution, so a possible valuation that will make this constraint true. So for instance, I have that P and Q are both of them false. So suppose that now I get rid of these constraints, so I'm not anymore considering that P needs to be equal to Q. And suppose that now I add a new constraint, saying that P needs to be not equal to Q. If I ask again whether there is a solution, there is, and the tool says that if P is Q, sorry, if P is false, sorry, and Q is true, it turns that this expression here, this constraint, is true because P and Q have different values. However, if I add another constraint to my system, and this constraint says that basically I have here that P, if P implies Q and Q implies P, I want a scenario where this does not mean that P is equal to Q. And this is unsolvable because if I have that P implies Q and Q implies P, uh, and P, Q being Boolean values, I need that both of them need to be equal. So if I try to run checksat here, I get as a result unsat. So there is no way of providing a valuation for P and Q that will make this assertion true. Since this problem is undecidable in a more general statement, Z3 can also return unknown as a possible output. So to conclude, uh, as I said, this is a very basic and introductory uh, presentation on formal methods. My intention was to show you some concrete examples of languages and tools. And I think the main message is that formal methods is always about bringing rigor to the specification, design, or verification of computer systems. And to summarize, my impression, my view is that B, together with these tools, uh, they are focused on the development of safety critical software, uh, typically with no concurrency, so single-threaded. The formal model here is a textual specification based on set theory and predicate logic. And using these tools, you can perform animation, for instance, supported by ProB. You can perform verification using both Atelier B and ProB. You can perform code generation using Atelier B. And you can also have some support for visualization using a tool called bMotion Web that allows you to create web pages uh, that are going to run under the hood your actual formal specification. Differently, CSP is a formal method whose focus is on concurrent systems. Its input is also textual, describing processes. So we say that's a process language. And you can also perform animation and verification using uh, FDR. Regarding UPPAAL, the focus of this tool is on timed systems. The input is a mix of textual specification and graphical models. So the timed automata are graphically designed, but you can also declare some operations, declare some global variables and some shared variables using code similar to C. And you have as possibilities again, you can animate these models, you can verify properties of these models. Uh, in Z3, the focus is on solving susceptibility problems. The input is also textual using the SMT-lib2 standard. And basically, it's aimed at verifying the satisfiability of these problems. If you want to read more about formal methods, I personally like these two books, chapter 3 mainly of this book and chapter 2 of this book. In my personal opinion, they give a fair introduction to the universe of formal methods. And if you want to get a more in-depth and practical perspective, I recommend you reading these two papers that have been published this year. So the first one uh, reports on a survey of professionals from Europe and North America working with formal methods. And this other paper somehow complements the first one, providing an expert survey, a survey with experts on formal methods. So thank you for your attention. I hope that you have enjoyed this brief tutorial on formal methods.
Thank you, Gustavo, for the great talk. Now we are open to questions. Please, you could submit the questions via chat. While the audience is thinking about the questions, I have a question about the B method. You said that it uses Turing provers, and sometimes some proof obligations cannot be automatically solved. So B generates code for proof assistants like Isabelle, Coq, in order to be proved manually.
No, as far as I know, uh, it has a prover by itself. So
Oh,
the tool ATLP provides a prover, a proprietary prover, and you can use it to prove your properties. So there are some proof tactics already implemented that you may invoke to solve the proofs with no user intervention. But when it's not possible, you can uh, edit the proof tree by adding hypotheses, proving them, and helping the solver to prove the original goal.
okay.
And what I meant by code generation is that you can generate, for instance, C code
Oh,
from uh, formal specifications. Actually, there is a distinction between an abstract specification and an implementation. So in the abstract level, you can use constructs like the ones I have shown you. So functions, non-determinism, and things like that. But when you go to actual implementations, you need to be more concrete, such that the tool can generate actual C code.
Okay, thanks. More questions? Please go ahead.
I'm seeing that Thierry is here. So if I said anything wrong, Thierry, please correct me.
No, it's okay. It's okay.
Okay, thank you very much.
Just to add one thing, yes, you said that we have a theorem prover, internal one, but we have also a connection with third parties theorem provers. So David Deharp from Weferini in Clearc is working on this, on the connection with academic provers and solvers.
Any more questions? No, I have another one. That's more a curiosity about timed automata. The notation that we use to represent the machines are quite standard from automata theory. That are just a question that I noticed that I could not see from your drawings of your graph representation of automata, if timed automata has a notion like a initial stage for the beginning of the execution.
Yes, it does. It's the state marked with a linear cycle circle. That's the initial state.
Okay. It's kind of the notation for final for acceptance state.
Yes.
Oh, from standard from our language books. Okay, thanks. There's a question, another question from Thiago. What's the role of logic for understanding all these models? How much logic do you think somebody needs to understand them in terms of undergraduate course?
Okay, I would say it depends on the method. So for instance, if you are using, let's say, CSP, since the CSP language is based on the CSPM language combines a functional language and this process language, actually you don't have, at least in the front end, too much logic. So you don't need to be an expert, for instance, on predicate logic for using CSP. On the other hand, if you're using, for instance, methods like P, where it's based on predicate logic, so your invariants or preconditions are stated using predicates, you need to have a fair understanding on these concepts to be able to write the proper predicates you want. So I would say it depends on the method. For instance, if you're working with UPPAAL, you would benefit when you want to optimize some analysis, you would benefit from a more in-depth notion of zones and clocks. And this is a concept that's not required, for instance, if you are using B or CSP, for instance.
Okay. I believe that we have no more questions. So let's thank Gustavo for the great tutorial on this introduction on formal methods. Gustavo, thank you for your presentation. Okay, just to end, tomorrow we have the opening of SBMF at 8:30 a.m. Brazilian time. So see you tomorrow.
See you. Bye-bye.
All right.